I got the video from Brooks and uploaded it.
Okay,
Sure,
thank you.
sure.
I know recording it. Yeah, I was doing it too little. I need to. I'm gonna read this.
All right, one of the things that we were, people talking about was voting on when the midterm would be, midterm examination. I let this be in your hands. Doesn't matter to me one way or the other, but, a lot of you probably take classes together, and you can schedule it at the best possible time, but there's never gonna be the perfect time. Somebody is gonna want it on a different day. Usually I have you vote on it. So, what I'd like to do is this Wednesday, you give me some dates that you like the midterm, and then, we'll vote on it. Now, fall break is Thursday and Friday, right? All right, so, by the way, there's water dripping right there off that vent, so please don't sit there. There's water dripping there too. Did this just start, or?
Somebody said.
It was there Friday. Yeah, obviously it was on Friday.
But I mean, so this has been this whole weekend, this thing's been leaking?
I think it's been a few weeks. We've seen water on that weekend.
Hey, John, would you do me a favor? Could you go upstairs and tell Dr. Nelms in the main office that we have a leak that it seems to be unreported? Just let him know. All right, thank you. I don't think I've ever had a leaky classroom. I've had a flooded classroom, but never a leaky classroom. Is that ceiling sinking or anything?
I see what looks like kind of like a puddle, like a water stand.
Is there a puddle down there or anything?
Drops on the.
All right, just leave it alone, but if they don't know about it, they can't fix it. And I have a bad feeling, nobody's mentioned this, because on Friday, I thought it was just a fluke. I thought it was from air conditioning condensation or something, but I don't think it is. By the way, is that air vents on? Yeah, turn it down. If you want to, you can leave that door open too, for as much airflow as possible. Okay, so remember, on Wednesday, we're gonna vote on when your midterm is, okay? And you'll give me some, possible dates, and then we're gonna vote on it. It's the only fair way I know. I think we've done polls in the past online, but it's better to have it in class. If you wanna discuss a date and argue amongst yourselves, you can. That way, everybody will hear the benefits of one day or another. So, we're doing, by the way, any questions? I put the quiz solutions up. Did y'all see? They're on one. And I haven't uploaded the grades on Canvas yet, corrected grades. Now, what I'm planning to do after this class is, if I need to, I'll talk to the people that run the Canvas support. But when I try to upload, and it's in a comma, it's a CSV file, it's not an Excel file. When I try to upload it, it will either tell me that there's been no changes, or that my header is not right. Now, I'm trying to look into this, and other people have had that same problem. So what I'm gonna do is go to the people, or the experts, and they can upload it. Just send it to them. Okay. So any questions about any of the things we've done so far? We're on arrays. Good one. Anybody? Huh? Okay.
So an end-fire antenna array consists of 10 lambda/2 dipole antennas.
So n is the number of antennas, it's 10. Their length is lambda/2. Go ahead.
And their space lambda/2 apart.
All right, so now I'm just trying to sketch something out. So they've got 10 antennas. They're all spaced lambda/2 apart. And we're gonna call this axis just X3. Go ahead.
There's a phase shift 9 degrees.
Alright, so the current is out of phase by 90 degrees, so if this is I naught, this is I naught e to the J 90, this would be I naught e to the J 120 and currently 180 and so forth. You all follow me, class? Now, what else?
So we actually plot the radiation pattern and then find the maximum end-fire power density at a distance of 10 kilometers and it's driven by 10 amps. Current source is 2.45.
Alright. Now, I wanna say this. The deal with this whole thing is, when we're plotting the antenna pattern, these antennas are dipoles, but they're perpendicular to the board. Now, please listen to me. I'm gonna try to be as clear as I can when I put down the field equations and power pattern due to this array. The dipoles are perpendicular. I think it says something to that effect. What he's saying is the dipoles are out of the board. That means if you think of a dipole antenna, its field pattern varies versus the actual angle to the axis. It has a maximum this way. These are out of the board. They have no difference in the amount that radiate. Each element, it radiates in the plane of the board. You all see this? This is a typical, it would be a navigational radar, typical type of thing that would be on ships. So the antennas are perpendicular. Now the array here, there's 10 of these things, and they each have an angle, phi or phi, right here. Now please hear me on this. Last time, I went through a long proof, and I showed you a few things with geometric series, and it all came down to the net E field from an array, the total E field, was equal to the E field of the element. This is the element's field pattern. Then it's times the actual array effect. I'll call it E array. Alright? Now the element would be like if it was a short dipole, it would be J eta beta I times sine of theta over 4 pi r e to the minus J beta, or e to the minus J beta r. That would be the element pattern. This E array is this. It's going to be the sine of n psi over 2 over the sine of psi over 2, where psi is equal to beta d cosine of phi plus alpha. Now this is in Whitworth's book. Alright? This is the alpha, this is the alpha. It has to do with the actual angle between the array axis and the actual direction that you're in. Do y'all follow me, class, on this one? Now, this doesn't have any, it's not a function of R, it's not a function of the current, it's a function of nothing else except the spacing between the antennas, the phase shift per element, and let me try to make this a little bigger. Psi right here is equal to beta d cosine of phi plus alpha. The separation between elements and the phase shift. We're assuming that the phase shift is consistent across here. We're also assuming that the current magnitude on each one of these is the same. You all hear me? Yeah.
The D up there, is that the same as L over here?
D is this. It's the separation distance between elements. Okay. So in our case, it's lambda over 2.
Okay.
Now that is for the, this would be the electric field pattern. Our electric field pattern for this one, now I gotta tell you, the electric field pattern is not a function of phi. Y'all hear me? It's only a function of the axis. If you look out of this board and measure the axial difference this way. But they just want the variation that would occur in the plane. Y'all follow me on this? Now, when we do this, this is what it would be for the electric field. I call it E array. Sometimes it's labeled as small f, doesn't matter. For the power pattern, listen to me now. When we get the power pattern, this is P ab. Now that's going to be equal to the power pattern of the element, one element. So the P average of the element, and then it's times this squared. So it's times that squared, or it's times the sine of n psi over 2 over the sine psi over 2 squared. Now, in Whitworth's book, what he does, he labels this as f of theta. He calls that sine of n psi over 2 over sine of psi over 2 squared. And if you look in his book, I'm trying to think of what page this is on, but well, he actually calls it, he calls it F array, and this is equation 8.101, if you look at, on page 474. Just take a look at this. Now, please hear me on this one, this is important. For ours, the only thing we care about is this right here. We just care about how that's going to actually map out, all right? Follow me? And we need to do it not in terms of psi, but in terms of theta. Okay, everyone? I mean, this is really f of psi that I put in here, but we need to make it f of theta. And remember, theta, not theta, it's phi. Phi is right there. Now we're going to examine this variation, this pattern. I want to show you something. By the way, some of this gets a little tedious, so you've got to stay sharp here. When I look at this pattern of just the sine, and I'm going to just take magnitude, sine of, say, psi times n over 2 over the sine, magnitude of sine of, really sine over 2. If you take a look at this, I'm going to say this is likened to the sine of x, all right, and I can call it, no, I'll do it this way. Well, I'll do it this way. If we look at sine of n psi over 2 over the sine of psi over 2, if n is large, the good question is, what is large? Well, I don't have a great answer for this, but something over 5. That's what I'm going to just go with. So if it's over 5, n large, we take a magnitude of this, then this is approximately equal to just the sine of, and I'll put it n psi over 2 over just sine over 2. Y'all follow me? And the reason that is because sine of a small angle, and this should be for psi small. Just try to understand. I'm trying to do this, trying to just be near the point where it's 0, the argument's 0. When you look at that, that's a sinc function type of relationship. Y'all follow me? So if you were to plot that, you would see this kind of deal in magnitude. The peak value would be n right there. The first 0, and I'm just trying to make clear on this. What's the first 0 of this function? Well, where's the sine? Really, we just need to know where the sine is 0, right? If n is large, so where's this? Well, n psi over 2 would be what? When is sine 0? At 0, right? But at 0, use L'Hopital's rule, you'll find out the value would be n. Where's the next 0? At pi, isn't it, class? So if you look at this argument, if you take n psi over 2, put it equal to pi, plus or minus pi, then you get 2 pi over n is the value of psi that would be the first 0. Now that will be the same as this over here. And I want to do something. I want to put that a little higher. So if I plot the magnitude of sine of n psi over 2 over the sine of psi over 2 here, just in magnitude, it'll start at n. The first 0 will be there, 2 pi over n. This 0 will be a minus 2 pi over n. Y'all follow me? It'll be symmetric, so that's the first 0. The next side lobe is down, this is a basic sinc function. It'll be down by about 13.2 dB. It'll be less. This 0 will be at 4 pi over n. This one will be at minus 4 pi over n. Y'all follow me? And the progression, the ripples will get smaller and smaller, and it'll keep going, then they'll repeat. All right? That's the way these functions look like. Now, when you take a look at this particular function, the main beam right here, and this is versus psi. I mean, the peak of this thing is gonna be when the argument is 0. Do y'all follow me? Alright. Then it goes to 0 here, and it goes to 0 here. Now you come over here to this equation where we have psi is beta d cosine phi plus alpha. They said the phasing was 90 degrees?
Yes.
Alright, so remember, we have psi is equal to beta d cosine of phi. Well, beta is 2 pi over lambda, right? D is lambda over 2 cosine of phi plus alpha, and alpha is pi over 2 if it's 90 degrees. Do you agree with me, everyone? How many see this, what I'm doing here? I'm just trying to bring you to the point where we can appreciate that in terms of phi, but you have to see the relationships. The first 0, remember, the peak is at psi equals 0, right? We're gonna figure out what that translates in terms of phi. So I put down 0 here, and now I can see what happens. You can see, first of all, we can get rid of the wavelength, right? That cancels. Then I have pi divided by 2 times pi, or this equation becomes flat. And the pi's go, so really I get 1/2 is equal to cosine of phi. Now just take a look at that and convince yourself that that's correct. Do y'all agree with that? Think about it. Divide everything by pi, right? The wavelengths cancel. Y'all, it's minus. Oh, right, minus. My bad. You're right. Does everybody agree with that, class? All right, what is that value? Well, cosine's an even function, right? Correct, class? Where is the cosine equal to minus 1/2? Think about it. What does a cosine function look like? So it's minus 1/2, right? Is that 135 degrees? Y'all agree? It's a well, 90 is 0, isn't it? 135 would be negative, wouldn't it? Because it goes to 0.
Would be 120.
Is it 120?
135 would be square.
Yeah, you're right. You're right. So it'd be 120 degrees. I think you're right. 120 degrees. Right. All right. Now that means when we take a look at our antenna pattern, I'm going to erase this and put the antenna back. What does he ask for, by the way? All right. We can only estimate that, but on this board.
Plot the
Here's-
radiation
huh?
pattern. It says plot the radiation
That would
pattern,
be what
find
mathematics-
the
yeah.
maximum
You gotta
entire
use
power
math. We're
density.
fine with the maximum value. So we know for this one, if this is my angle, phi, when phi is 120 degrees, or basically now my maximum is going to be out here. And I'm going to give you an exercise to turn in. So the maximum would be at 120 degrees here. That's going to be the maximum. Now, I can estimate the lift too. Remember I told you that the first null is at 2 pi over n, right? Y'all follow me on this, class? So now I can come back to this equation, right here, and I can say 2 pi divided by 10, right? And it could be plus or minus, by the way. Y'all follow me? It'll be symmetric about the main beam point. Is equal to beta d, well beta is 2 pi over lambda, d is lambda over 2, so that's just pi, isn't it? Right there? If you go ahead and do the math on this one. Do y'all agree with me, class? Then it's plus alpha, which is pi over 2. I'm just putting down the numbers on this one, and I should put the cosine. Cosine. Because that's what we want, plus pi over 2. I'm only going to do the plus part here. Now when you take a look at this, what happens? I can get rid of pi everywhere. Do you agree? It appears on both sides of the equation. So now I have 1/5 is equal to cosine of phi plus 1/2. The 1/2 comes off to the other side is minus 1/2, so I have 1/5 minus 1/2 equals cosine of phi. And that's going to be, that's 2 minus 5/10, so it's minus 3/10 equals cosine of phi. Can you give that to me? What is the inverse cosine of minus minus 23?
107.5 degrees.
Okay. So this is 107.5 degrees, that's the first null. And I'm gonna tell you, when you plot these with MATLAB, it shows the whole thing in heartbeat. But I'm just showing you the way, back in the day, you would do this. And the way Whitworth probably at least wants you to have an appreciation for it. Now that's gonna be the first null, so I know the main beam's gonna look like this. Something like this, and we can figure out where the other point is, but it should be symmetric. Whatever that distance is, you take 120 minus 107.5 and subtract that. If you add it to where the main beam is, that will be the other angle, almost guaranteed. Y'all follow me, class? So that's the main beam. Then you're gonna have these side lobes. Let me actually draw this over here. I'm just trying to do a sketch of what'll happen. So the power pattern, it'll look like this. If the array is here, and we were just doing a polar plot of the power pattern, it would have a peak value at 120 degrees, so it came out and had this as 120 degrees. Then you would have this. Then you're going to have these small side lobes here coming off. And the first side lobe will be down by minus 13 point, about 3 dB. Yeah, 13.2 actually, dB. Now that side lobe, remember, if it's power, it's 10 times the log of the power would be down by that much. If it's voltage, it's 20 times the log of the volt, or E field. All right? But just, I'm trying to give you an appreciation for this. Now, this particular problem, you can't get a plot that's a good estimate without, yeah.
Just clarifying, that angle 107.5, is that measured from the right side?
Yeah,
No,
it's
on
from
the
here to
other-
here.
On the other graph, because where you have it is
Oh,
107.
this should be, this is 107.5. It's measured to there. And so it's got a fair, what is that? What is the beam width on this roughly? And this is to null, it's not to the 3 dB point. The beam width is what, 120 minus 107, call it 108? It's about 12 degrees, right? A little over 12 degrees. That's, actually that's to null, and you'd have to double that, so 24 degrees null to null. Does he have something like that for the null to null beam? Does he have null to null beam within that one? I don't know. What is his? Well, he plotted it.
Yeah, I used MATLAB for it.
But what did he get? He should say null to null beam width, it's typical. Or peak to null, one of the two. Peak to null would be about 12 degrees. If he does he just show a plot?
It's just a plot.
All right, when you plot that one, here's the deal. The only thing you're really plotting is this right here, the sine. He's gonna plot power pattern, I think, in his. Is just the sine of n psi over 2, sine is psi over 2 squared, where psi is this. So you create a vector for phi, create a whole bunch of values, then, right below it, create a whole bunch of psi values, then plot the actual value of this function, right here, versus phi in a polar plot. You all know how to do polar plots? How many do? Have you not done polar plots, guys? You don't know? I will send out a program, for a MATLAB shell script that'll be able to show you how to do this, but he should have the program there, does he?
It's in his book, Permanent Bag, but not
It's in the chat.
He has that? I'll send you one. All right, but it's going to be a very narrow beam. Now, the thing is, when you have 10 elements, the power pattern goes up by a factor of n squared, as far as the gain goes up by n squared, and the peak power densities go up by n squared. So that's 100 times the power density you would get from a single element without the array. Y'all follow me? And the beam width will be very narrow. I'm going to give you some problems, and here's the deal. On Wednesday, it's a strictly extra credit. I'm going to take this assignment, grade it, and I will put that, I'll replace your lowest quiz score to date with that, all right? Now, it's not a hard thing to do, but you have to force yourself to do it and show up on Wednesday to hand it in, all right? Don't mail it to me. And I did, you won't believe what I see sometimes. No matter what I say, they will email me everything, and they'll say, I couldn't be there because I'm down in Florida, or I'm in Alaska, or whatever. But please just bring it. Try to get you here too, just for the record. Try to also give you a reason to be here, because I know fault rates is great. Any other questions about this? Because really with the array business, this is the deal. You've got to plot that, it's too complicated really to do an excellent sketch for anything more than 2 or 3 elements. And power goes up as the square of that function. The E field goes up just as the magnitude. And you remember that, you won't have any problems. Now, the gain goes up by a factor of n squared, peak gain. Remember that. Okay. I'll give you an extra pair to sign up. Anything else? Yeah.
Is there an efficient way to estimate the half power beam?
I'll tell you, if you want to do this, what you have to, you can do it, but here's what you have to do. This is going to have a value of n, all right? Peak value on this side. Well, you take n over square root of 2. Now that would be for the E field. When you square that power, it would be n squared over 2, right? Take this, just take n over square root of 2, and then solve for what psi value gets that. Once you have that psi value, you plug it in here, and you'll find the value of p. But I'm going to tell you, when you're doing arrays, it's usually null to null. You care about. With single antennas, it's the half power beam. And it's just because these things, the beam width gets very narrow. You're going to see the beam width on this thing's probably about 5 degrees, maybe 10 degrees at most. It's very narrow. It concentrates it.
So for something like this, if we have just a single row,
It's called an array.
Yeah, just a single array, not a 2-dimensional array, just a 1-dimensional
Right.
array. Are we using is that going to typically be used just to transmit a particular direction, or are you gonna
Okay.
phase this, like electronically scan it? Or?
Yeah, you will electronically scan it. They will electronically change that phase shift on each current, it'll steer the beam. And then they will let it broadcast however many pulses you want and listen at that same angle, then move on to the next angle. But at electronic speed, so you're talking about microseconds, tens of microseconds. They can do this very efficiently. This is something that when you get into radar and antennas, you see all this. But I have to mention a few other things about arrays. This is called a linear array, all right, that has equal space. It's a single linear array. So they have this. Now, hear me on this one. This one you're going to have to know for any kind of quiz like this. Whenever you have this, and this is important, if the main beam is shooting off the end, if all of a sudden the main beam or the peak value where most of the power is going is off the end, that is called an in-fire array. Makes sense, right? That's an in-fire array because it's shooting the power off axis. All right? If the power is coming out with a peak power in this direction, where you have this effect, that's called a broadside array. Anybody want to guess where that term came from? From where?
Ships.
That's right, from the old nautical days when they came to fire, they bared their guns, they would turn broadside, so all their cannons could be launched in the same direction. That's called a broadside. And that's where this term came from the Navy, from back in the day. This is an in-fire if you're shooting the power off the end of the array. Those are just two terms that you should be at least familiar with, in-fire and broadside. For this type, if you want this, you want a broadside, can anybody guess what the phase shift would be? Think about it. 0, right? There's no distance difference in the radius vector, right? So if you don't mess with the phase, they're all constructively interfering there. Y'all follow me? Then, when all of a sudden you're getting something where you get a total, the total amount of constructive is equal to the destructive phase shift, then is your first null, and then the next time where you get mainly constructive interference is going to be your next peak and stuff like this. But I don't want to spend too much time on this because this stuff, when you're talking about array antennas, I got to tell you this. This we've assumed just constant current, right? In the real world, they will change the magnitude of the current and the phase to maximize what they want. Sometimes they want no side loads. They can do that like that. They can also change the spacing to optimize certain things. One thing that you should at least be aware of, whenever this spacing gets greater than lambda over 2, you will have two main beams between 0 and 180 degrees. And that's called something that causes a problem of ambiguity. When you go beyond a certain scan angle. When you're standing straight up, it's not a problem. But when you come over a certain angular distance, and it depends on how far, then all of a sudden, you'll get another main beam, and the pattern will repeat itself. And you can't tell when you broadcast and listen if the signal came from over here or here because of that. So if you want no ambiguity, no problem with the array scanning and the pattern replicating itself, you have to have D greater than lambda over 2. Some of this might seem it's over your head, you don't really appreciate it. I'm just telling you things you should be aware of. Believe me, you will appreciate this when you start messing with antennas. I hope that makes sense. Wentworth's book does not get real deep into this. He just basically gives you enough information. So if you have to, you can do a pattern for a linear array. That's basically it, where there's constellation. Do you have a question?
So if broadside has 0 phase shift, would fire have 180?
Well, infire depends on the spacing, but infire will make sure that the total phase shift, the peak and constructive interference will be this way. So if you think about that, if we want an infire array, if we want the maximum to be there, then what would this phase shift have to be? I want to just do a thought experiment. Well, where is this function going to be? Where is that the maximum? Class? Psi equal 0, correct, class? That's the maximum value, right? All right. So if this is 0, all right, and you want to know, you want to find, you're saying this angle right here is going to be 0 degrees, right? The cosine of 0 is 1. So let me just do this. 0 is equal to, that's pi plus alpha. You agree with that? Isn't that right? So what is alpha? Minus pi, right? So that would tell you the phase shift that you would do if it's lambda over 2 apart.
Okay.
Right? But the spacing is critical because as the spacing changes, that value of alpha changes as well. Always remember the peak where the main beam is going to be when when psi is equal to 0. That's the key. Okay.
Well, you typically see in a real radar or a real antenna or something like that.
An array.
In a real array, your broadside beam will typically be a little bit better, have a little bit stronger gain, and your fire will be super.
Oh yes, yes. You're getting into the weeds here, but the narrowest main beam is when it's in broadside. That's when the beam width's the minimum. As this scans this way, there'll be broadening in the main beam. I mean, this is getting into antenna theory a little deeper than I want to. Normally, I'm doing a full lecture on antennas. I mean, this would be after you come out of EMAG 2 in the radar class, or I don't think I do an EMC, but in the radar class, I take you through everything. I go through a linear array. I show the scans. I do all that. Show you how the main beam broadens, how to estimate the amount of broadening, do all that stuff, the whole 9 yards. And I do a lot of these things with MATLAB programs on the screen. I don't even have plugins for this thing here. I just noticed that. I take it back. They do have an HDMI, so I could probably I'll show you some of these things maybe on Wednesday. I go through the whole 9 yards of this, but at this level, with the amount of material we have to cover, we can't get into all that. It's a week at least of going through problems and just development. But you'll get some of this in antennas, definitely antennas, and you'll also get it in radar, and probably in some of the other upper level courses, but I can't tell you all of them. All right. Now, any other questions before I move on? Did you have another one for me, by the way? Because the MATLAB one you got to plot. All right. We've done freeze, we've done radar, went through Doppler too. I think we're good with this chapter. Now we're going to get into chapter 9, and this is EMC. And what? Go ahead.
Will chapter 8 kind of conclude this stuff for
That's
what
it.
will be tested on, or will we include chapter 9 stuff?
Well, it depends when you decide on the test. All right. The way it goes with this class, you're responsible for everything up to the lecture before the exam. So, I mean, you can put the exam up to the last week of class if you want, but then you're responsible for a lot more material. So that's how it works. How many have had me before? All right, well, you know the drill. Just ask, look at the people with hands up. They will tell you how I test. Tests are based, when I make up tests, I go through the homework, I take a look at what we talked about in class, but primarily the homework. And I don't ask you anything you haven't seen. And I'm not gonna ask a whole lot on kind of theory, except maybe. I might ask something with an array where the main beam is. I mean, where's the main beam directed? And that's really that. Finding out size 0 and then solving that equation. All right. So for EMC, this is chapter 9. Let me tell you about EMC. It's electromagnetic compatibility. Typically, it's called electromagnetic compatibility and interference. It's about, and these guys that are EMC, EMI engineers are some of the highest paid engineers on the planet. I know some of them personally. The reason is this: when you design a product, I'm going to just fictitiously say say Adtran or Dynetics design a product that's going to be out there in the field, and they go out and test and do everything on it. And then they put it in the field and they find out there's a large failure rate. They're getting reports back, and they made 1 million units of this at like thousands of dollars a unit. It's just a sizable amount of money. And they don't know what to do about it, because it's going to cost them a whole lot of money to call those products back and try to troubleshoot them in designs from scratch. So the EMC engineer comes on the scene, or EMI, and he goes out and he assesses the damage. I was involved with one of these things personally. I wasn't the guy that designed this fix, but I was there. And this was a lightning protection problem on a chip that came from Adtran. That thing is still dripping, by the way. It looked like it almost got you on the head. I mean, if you need to move, please do. Anyway, so lightning would hit these cell phone towers, and they had lightning protection equipment installed, but the equipment didn't protect the device. The device protected the lightning protection equipment. It's supposed to short the current and strike the ground, but it didn't. I told this in your class. So what they did was they get the EMC engineers to get out there in EMI to come up with an in-field repair. So how do we repair it in-field? What do we ship them at lowest price to do that? Those guys are worth their weight in gold, because they have to have an understanding of all the theory behind antennas and all that, have to understand the product and what can cause a problem. In that case, it was common mode currents, which we will get into more in a bit. And the guy did find a way to actually develop a lightning protection add-on that was relatively inexpensive. These guys make $500,000 and up a year. I mean, they're very highly paid because they're so valuable. And anytime you get something in the field, I mean, you already put it out there, and you got millions of units, and then they start failing one after another because of lightning or whatever. The guy that can repair that on the cheap is the guy that's worth his weight in gold. He's probably paid as much as the CEO a lot of times. I mean, that's how good they are. But there are also not a whole lot of them. So if you want to find an interesting career path, think about that. You can read about it. Clayton Paul was a very famous guy in this. There's all sorts of stuff. Now, in these days, I don't know where the biggest problems are, but I can venture or guess that with the amount of autonomous vehicles and actually drones and all that other stuff, there's going to be something that's going to cause these things to fail at a cataclysmic rate at some point, I think. I'm not sure of this, but I have a hunch that there's going to be some more problems the more they get in the field. The person that can be there before can know what's going to happen in the failure. I've already read about these things. They've had problems with Tesla and other things that are really causing people concerns, because they're great if they drive, but you know what? These are machines, and they don't adapt very well to the unknown, so things can go wrong in a big way. That's the idea with EMC. So first, there's two types of EMC problems, usually are categorized this way. One is radiating emissions, or either a product is vulnerable to something radiating on it, or it's radiating an illegal amount of electromagnetic energy. And the FCC in this country, the Federal Communications Commission, dictates the limits on that. In other countries, in Europe, it's CISPRI. In the military, they have MIL standards that they have to meet, which are much more, the requirements for the military are much more difficult to meet than they are for the civilians. Now that's radiated emissions. Then there's something called conducted emissions. Conducted emissions are in and out of that wall. You may not know this, but when you plug in a product, you actually do cause some of the high frequency from the digital systems, some of that high frequency voltage and current is actually pushed into the wall. And it can cause problems. Now you said there's 110, 117 volts RMS at 60 hertz there. How can that cause a problem? Problem is when you plug in other devices, especially in hospitals, that high frequency stuff comes out. It'll pass by the transformer a lot of times. You gotta understand something. And it'll get on the actual circuit board. That's a conducted emission problem. That is a big problem. Now with conducted emissions, there's filters you can put in there and all sorts of stuff. There's ways to beat them, but they are a problem. Radiated emissions, for the most part, you can deal with just by putting a whole lot of metal around it. This laptop case, probably most of your laptops are not metal. Some of them are. But this laptop case is metal, all metal. And it's sealed. It's almost EMI proof, not quite. Right? There are seams on here and stuff like this. But it's designed very well. It's to shield against EMI. It doesn't radiate much either. I've got one at home that's vulnerable to everything. It's an older Lenovo. Anyone with a screen where you can't shut that?
I got it.
All plastic.
I got all plastic.
Yeah, I want to just say, I say it's vulnerable. All right, well, yes and no. This is a digital system. Everything in there is it's based on a battery operating system, and most of the stuff's shielded. However, that is much more susceptible than that one. I'm just leveling with you on this stuff. I don't have a lot of experience in this, but hospitals, I'm told, and I've been in hospitals, and you can't usually, they're shielded very well. You can't even use a cell phone, like in the operating rooms and stuff like that. Does anybody know about this? It's done that way for a very important purpose, because there's a lot of monitoring devices and stuff are very sensitive to any type of radiated emissions. They have a much higher standard of what's allowed, I think, to health professionals in their environment than others. I'll say one other thing before I go down this pipe. There are two types of radiated emissions tests, generally speaking. There's a 10-meter test and a 3-meter. 10-meter is for industrial systems, like if you go to West Point Pepperell, something like this, a mill. They'll have much looser restrictions in what can be used in that environment. It's not designed for anything other than building things, and they've got a lot of sparking and everything already. In the residential areas, the testing's done at 3 meters, and there's tests, and it's frequency-dependent tests. And they basically are much more restricted in residential areas, what you use in your home for any kind of radiated emissions. Now, I'll spend more time discussing this as we go down chapter 9. But for now, I just have to give you a little background why we're doing what we're doing. So we have to begin by talking about passive elements and what passive elements look like at high frequencies. Ideally, when you get a resistor, it looks like a resistor at all frequencies, but that's not true. When you see a resistor, this is the symbol we use, right? I mean, that's just a standard symbol. It could mean, a resistor can mean, believe it or not, a light bulb is modeled as a resistor. A heating element is modeled as a resistor. You're used to these little carbon resistors, the 1/8 watt, quarter watt, but they have the bands on them, right, for your printed circuit boards. That's a resistor. That's very commonly, if you open up, maybe not your phone, but if you open up a lot of your electronic devices, radios and stuff like this, TVs, you'll see those carbon resistors used. And then when you think about this, so we don't know what this is, we just know that's the symbol. It's supposed to just cause resistance. But anytime you have a resistor, you have a voltage difference across there. Now, anytime you have a voltage difference between any 2 points in space, you have a differential amount of charge or capacity. So all these actually are modeled with a parasitic capacitance. Something you would like not to have, but it's inevitable, it's there. If you have a voltage difference, if current flows in there, you develop a voltage difference, you have a capacitance, small as it may be. Now, anytime you have wire in current flowing, you have a magnetic field. Anytime you have a magnetic field, you have magnetic energy in that field, and that means the way, when we do this in circuit analysis, we develop a part called an inductor, and we know that 1/2 Li squared is the magnetic energy, and this is going to be the lead inductance. Again, you would like that not to be there, but it is, and you can't get rid of it. When you look at this element as a whole right here, we're going to look at the input impedance. Before I do, I have to say this. when you were taught soldering or whoever did your laboratory work, did they tell you to cut the lead links down to a minimum? How many heard that before? Please remember that. Always get them as short as possible, because it'll reduce the inductance that you don't want. The second thing is always use the minimum amount of solder. Please, they used to call them solder suckers. I don't know what they call them now. They got wicks and stuff like this. You want to use the minimum amount of solder. Believe me. So this is what the resistor is modeled as. Now, there are higher level models. This one works pretty well. And I got to tell you one other thing. Because you got wire here versus frequency, there's also an AC resistance that changes. There's other changes. This is a first order model. When you look at this, you would say Z into this one would be equal to, well, it would be equal to just J omega L. Do you agree with that? And that would be L in the lead. And it would be the parallel combination of those two, which is 1 over R, plus, and it would just be J omega C parallel, right? And then you could multiply by R, and you would get this. And you have 1 plus that. Do y'all agree with this, class? I'm just trying to show you. You can find out what the impedance is. Now, if you went and you plot that, because I'm running out of time, the way they normally do this, and you take a look at this, they'll take the log of the frequency here, log of F here, and on this axis, they'll plot 20 times the log of the magnitude of the impedance. This would be Zn for that resistor. Now, all the elements I'm going to show you at low frequencies look like what they're supposed to be. So that resistor is going to look like a resistor. Just take the frequency and let it go to 0. If omega is 0, that goes away, I have R. You all follow? It will look like basically 20 times the log of R, whatever that is. It doesn't matter. Then, when it hits this point is going to be 1 over 2 pi times R times C parasitic. This is the first F1. It'll start falling by minus 20 dB per decade. Let me explain where that comes from. If you look over here, and if you remember Bode plots, you know the Bode plot, any of these poles turn on when you get 1 plus J1. Do you all remember that? Well, if you take omega times C parallel times R equal 1, alright, you get 1 over C parallel R, and omega is 2 pi F, so if you multiply this by 2 pi, you get F. That's where this break frequency happens. It's the first break frequency. It's going to fall down at minus 20 dB per decade until you hit this frequency, which is called the self-resonant frequency, F self-resonant. Now, that's equal to simply 1 over 2 pi square root of L lead times C parasitic. Now, do y'all remember back in the day when you had circuits, you knew the resonant frequency of an inductor and capacitor in series or parallel was just 1 over 2 pi square root of LC. How many remember that? I think most of you do. Yeah, Erwin especially. All right, and that's important. All right, that's called the self-resonant frequency, and that's the lowest value that you can get of impedance. Then it starts going up at 20 dB per decade. Now this is in Wentworth's book. Let me see if I can find it real quick. I'll come back to what a wire is and stuff at another time, but
Did you find one the thing?
he's got in figure 9.7 on page 508, but he has the LX. You don't need that. It's just really the lead inductance and capacitance that's in parallel with the resistor. He doesn't show the approximation that I did, but that's the way it's usually done. And I'll give you more information about that, but that's what he's trying to show on 509. The real thing to remember is this is the self-resonant frequency. It's just the resonant frequency of an inductor and capacitor, and this is the first break frequency. That's what starts breaking. You remember those two things? That's how you do this problem, and I'll give you problems like this to do. The next thing we talked about, I'm doing the elements, I'm not doing the wire, it's gonna be a capacitor. Now, when we do a capacitor, and he has these models in there, he doesn't show you the bogey like that, but that's the better way to do this. When you have a capacitor, well, it looks like a capacitor at low frequencies, go figure. But when you have a capacitor, there's wiring and stuff like this, and you're going to get a lead inductance and stuff like this. And let me show you where this is in his book, because it's better to just look at his book on some of this stuff, so you can have an appreciation. So this is on page 514, and it's at the bottom of page 514. I'll make mention of something also. There's one other thing in here that's important. So this is what the capacitor looks like ideally. But again, anytime you have a lead and current flowing through it, you have magnetic energy, and therefore you have an inductance. So this is L, and it's really for the lead. I'll just put L sub L, but it has to do with the wire itself. Now, anytime you have current flowing in a wire, you have resistance as well. There's some resistance, and it would be an AC resistance with a high frequency in there. So there's going to be some resistance. And that's, I don't know what he calls that. It's not one, so it's parasitic, but I'm not sure if he uses sub P for that. RX. I'm not sure I like the X. This is unwanted, but, and that's what it looks like. Now, that's ideal for mica capacitors, for most small, incapacitors with a small form factor. There's one exception to this, and these are electrolytic capacitors. How many have heard that term? An electrolytic capacitor has kind of a gooey chemical in there. It's really something that's not quite solid, not quite liquid, right? It's in there. And the reason they use it is as a very large dielectric constant and a fairly high breakdown voltage. It can store a lot of energy. Thing about an electrolytic is you can't put current, you can't change the polarity on it, right? Can't be used for anything where there's going to be an AC type thing. This is used to get rid of like ripple voltages on DC that you don't want. It'll damp them out. Electrolytic capacitors blow up if you try to put current through them in the wrong way. In other words, if you get full cycles, it causes the actual dipoles in them to flip, they heat up and blow up. And I've seen the aftermath of one of them over the physics book years ago. And they can be, there's a high energy laboratory. Those things, when they blow up, they can kill people. So it made me very aware not to blow up electrolytic capacitors. Don't do anything dumb with them. Now, if you had an electrolytic, then there would be a resistor that would have to be put across there for an electrolytic. I'm not going to ask you about electrolytics, but understand they have a leakage resistance. It's not trivially small. So you have to include that. If it was electrolytic, you have to put a resistance there. They are leaking, but that's okay. This is the actual model for this circuit. Now, if you take one look at this circuit, remember it's a capacitor, just one look at it. What do you think the plot's going to be of the impedance? If this is log of F versus the magnitude of the Zn right here. Y'all know, give me 1 second. Just take a look at it. Well, what would it be? I'll write it down. Zn would be what? 1 over J omega C plus J omega L plus R. Do you agree with me? Rx in this case. Isn't that right? What is that value as omega goes to 0? Take one look. Anyway. Infinity, isn't it? Don't we have 1 over 0 here as omega goes to? Sure. And doesn't a capacitor have an infinite or its own open circuit exit? Sure. So what happens is it comes in, and it's coming in at a rate of minus 20 dB per decade. Now, it keeps coming in until it hits the self-resonance frequency. And that's simply 1 over 2 pi square root of LC, as the other resistor was, all right? And after that, it starts going up at plus 20 dB per decade. So that's what the that's what the capacitor looks like. Last thing I'm going to say, the inductor is trivial. The inductor is just the inverting this. I know I'm over, so I'm going to let you go. I'm going to say, what time do you have, by the way? What?
52.
All right, I'm over by 2 minutes, right? I'm supposed to break up at 12:50, but for the inductor, the only thing that happens is this is inverted. And for an inductor, I'll just put it down for you. I'll show you the equation later. Log of F right here is this, where this is the self-resonance. 1 over square root of 2 pi, or 1 over 2 pi square root of LC. It's in his book. This is plus 20. This is minus 20. And there will be some standoff resistance there for the resistance of the wire. It'll be very small. I'll show you where those are. I'll give you some problems. We'll do the wire, what the wire looks like at high frequency, and also the AC resistance of it on Wednesday. I want to give you a special assignment. Bring in and I'll replace your lowest quiz grade. Okay? All right. Hope this made sense.